do you want to get started?
All good to go.
All right. So welcome everyone to our last DOC CCHF virtual seminar of the year. Today we have Professor Nuno Maulide of the University of Vienna and Neil Garg from UCLA. And I just wanted to point out, since this is the last symposium of the year, we will, be planning shortly our 2021 virtual symposium series. So if anybody has any suggestions in terms of speakers, timing, format, please feel free to contact us. And we'd be really happy to hear them. So we have a few announcements before we get to the talks. So you go to the next slide. We've kind of been talking a little bit about data throughout the year in various forms, making jokes, tweets, things like that. But I just want to point out that recently the Division of Organic Chemistry launched a data website. The address is shown at the top, organicchemistrydata.org, and it really has a variety of very valuable resources from reaction info, solvent data, total syntheses, things like that. Even some more fun stuff. A link to Not Voodoo, which gives you a nice little list of rookie mistakes that we've all made. My personal favorite being kind of at the bottom there, setting up a complex reaction and realizing there isn't enough solvent in the lab. But really entertaining website to go through and vote. But check out that if you're interested in or in need of finding common organic chem lab data. So moving on, I know what's been on everybody's mind lately, of course, is the election. And obviously I'm referring to the 2020 election for the Division of Organic Chemistry Executive Committee. And if you joined a little bit early, you saw some of the statements, the bio slides from a couple of the candidates. We have a lot of great candidates running for chair-elect, counselor, member at large, Catherine Lamont for chair-elect, Caitlin, Rick, Hugh, Catherine, Josh, and Michelle for counselor, and our own Scott, Diane, Kathy, John, Mike, Daisy, Kimberly, and Elizabeth, all running for member at large. So, if you haven't voted yet, please vote. You can find information about the candidates on the ballot and on the DOC website. So again, just putting a plug to please vote in that election and the national election. In terms of events that are coming up, I wanted to put a plug in for the Princeton ACS Fall Organic Virtual Symposium. This is a symposium that the Princeton ACS puts on every year, obviously usually in person. This year it'll be virtual. You can register at paxfolks.org. It is free this year, but they are limited to 1,000 attendees, and this is always a really great event. This year, Professors Corinna Schindler, Matthew Disney, Marty Burke, and Dr. Margaret Shute-Moyer will be speaking, so strongly recommend attending that. In terms of additional upcoming events, I think there's been quite a few questions on the ACS Spring 2021 meeting format, whether it's going to be in person or virtual. It's likely at this point that it's going to be a virtual / in-person mix. The details of this will be announced in October, November. We're starting to have meetings on that. The virtual platform, we believe has improved dramatically and can handle a lot of these symposia. As you can see, we have quite a number of organized and award symposia that are that are planned. The distribution we'll see over the next few weeks, but really in terms of organized symposia, we have just a very broad scope from presentations and panel discussion by LGBT chemists to on DNA reaction development, pharmaceutical sciences, high throughput experimentation. In terms of award symposia, we have this year really a bit of a wealth of awards. There were 25 Division of Organic Chemistry members who won national awards from kind of the usual that we see, things like the Corey Award, the Norris Award, Gunther, Brown, to a few that we don't always get, the Ola Award, the Breslow Award, the Earl Barnes Award. And then the and then the COPE Award Symposium, Industrial Young Investigator Symposium, Technical Achievements that were all rescheduled from the San Francisco meeting. So it should be a pretty nice symposium, pretty nice meeting, whether it be virtual or in person. So I'll turn it over to Scott to elaborate a little more.
Thanks, Steve. Welcome everybody to today's virtual symposium. Yeah, so this is a list of all the awards given through the ACS Division of Organic Chemistry this year. I'd like to congratulate all of the winners from 2021 that are listed here. Just actually way too many to go through in the short time that we have, but there's more information on the website and additional DOC awards listed on the website. And I'd like to also say that the nominations for next year's award goes through November. So if you have some people that you'd like to nominate, please go and do that by the end of this month. So like Steve said, it just congratulations to everybody. If you go, Rio, to the next slide, please. Right, so award near and dear to my heart, the Technical Achievement in Organic Chemistry. I'd like to congratulate all of the winners from around industry for their contributions and their award this year for the Technical Achievement, which is for BS, MS chemists and their outstanding contributions to the field of organic chemistry. This is open to industrial and government sectors. The nomination deadline for this one is the 15th of January, 2021, and those will open pretty soon. And Boozy would be from Corteva would be the chair this coming year. She was chair this past year and also again for next year. So congratulations to all the winners pictured there. And that's going to be a great symposium in the spring when we see it alongside the next one, which is the Young Investigators Award, which is for the Rio. Can you go to the next one? Yeah, thanks. Cool. So this is the Young Investigators from Industry Award. This is just a great class of folks here from all over industry, and really excited to see this one in person if we can. But if not, it's going to be a fantastic day for people to listen and to see all of these just the fantastic progress people are making on their projects and across industry in discovery process and other areas of industry. So this one will be, like Steve said, part of the spring ACS. However that goes on, whether it's virtual or in person. Hopefully one of these days we'll get back to in person. All right, and the next one is right. Okay, yeah. So another event that's coming up is the CCHF Virtual Symposium Undergraduate Edition. This is a new event that it's going to be held in about a week, next Tuesday, and that is presented by the CCHF as targeted towards undergrads, and their speakers will be Hugh Davies, Richmond Sarpong, and Karen Macbeth from Emory. And I'd like to just welcome anybody who's interested in undergraduate chemistry and who's actually actively involved in that to come and see what's going on from these speakers. Then the next one is another CCHF Virtual Symposium, which will be the monthly seminar shared by the CCHF, and the speakers right now will be Alison Wenlant from MIT and Magnus Johansson from AZ, and another speaker, which I think it will be, that's in December, will be announced before that. So that's another event coming up from the CCHF. Excited to see that. Right, the NOS 2021. Hopefully this will be one of the first fully in-person events that we'll have next year, pending hopefully things will be a little bit better for travel at that point. It's supposed to be taking place at UC San Diego. We have a wonderful lineup. Our chair, Angie Angeles from Gilead, has been taking this on and done a great job of putting together all these speakers. Ken Houck will be receiving the Roger Adams Award, and as you can see, it's just a amazing lineup of speakers highlighted by Frances Arnold, a Nobel Prize winner, and a lot of other folks that are familiar to many of those across the industry. So please stay tuned on Twitter to watch what developments there on NOS 2021, and we can start submitting your posters at this point. And like Steve mentioned, we're taking nominations for the next NOS, which will be in 2023. And so feel free to throw some suggestions out on Twitter to all of us, which is the next slide, I think. Yeah, here we go. We're looking for some sites that might have a big lecture hall on campus, housing and dining. Steve, I don't know if you want to say anything more about this one.
Yeah, so as we're looking forward to 2021 imminently, we're also starting to plan for NOS 2023. So Michelle and I will be co-chairing that event, and there will be an announcement in the DOC newsletter and on the website imminently. And we're going to be soliciting suggestions for locations and venues for the NOS 23. So 2023. So if anybody has any suggestions, please feel free to tweet or email either Michelle or myself. And if you have any general comments on the format or these virtual symposia in general, Carl, who unfortunately couldn't be here today, myself and Scott, or the Division of Organic Chemistry. So with that, I will move on to the introduction of our first speaker. So I want to welcome Professor Nuno Maulide of the University of Vienna. Nuno is originally from Lisbon, Portugal, where he obtained his chemistry degree at Instituto Superior Técnico, followed by a master's at the École Polytechnique in France. He did his PhD studies at the Université Catholique de Leuven under Professor Esteban Marco, after which he moved to Stanford, where he did a postdoctoral fellowship with Barry Trost on ruthenium catalyzed bond forming reactions. And personal note, I seem to recall a number of group pictures with Nuno in interesting hats. Happy to share them, I guess, with Nuno's permission, of course. Feel free to ask for those. After Stanford, Nuno began his independent career at Max Planck, and in 2013 moved to the University of Vienna as a full professor. Nuno's been extremely productive in his independent career with over 125 publications, with research interests from total synthesis to transition metal catalysis to the chemistry of sulfur-4, inamides, and amide activations. Nuno has been recognized with numerous awards over the last few years, and a couple of which are the 2020 Tetrahedron Young Investigator Award, the 2019 Scientist of the Year in Austria, and the 2018 Springer Heterocyclic Chemistry Award. And really interesting, and as I've heard firsthand, Nuno is an exceptionally skilled pianist. He gives concerts, and he's been a finalist in several competitions. Like our other speaker, Neil Garg, Nuno's also involved in the popularization of chemistry, and today he'll speak to us about making difficult bonds with rearrangements. Take it away, Nuno. Thanks a lot.
Thank you very much for this very kind introduction, Steve. You didn't say to me that pictures would be made available. I think you should actually consider selling them. Those kinds of things are not to be made available freely. Otherwise, I might need to ask my employer for a leave of absence or something like that. So it's really a pleasure for me to be here today and to have the opportunity to be a part of this last symposium, and also to have the opportunity to tell you something more about the research we've been doing in our team. I don't know if you can see the screen, but I imagine it might be projected right now. And indeed, as Steve mentioned, our group has been relatively active in the area of using rearrangements for organic synthesis. But today, I actually would like to focus on a subset of those rearrangement reactions, namely reactions where we mess around with the polarity of organic substances. And so you could have a little bit of a subtitle, "Don't mess with my poles." That allows me to actually delve into two areas of our group's research. One of them being amide activation, and another one a more recent interest that we have in exploring iodine-3 chemistry, precisely to achieve these kinds of reversals of polarity. If I dig into the first part of today's talk, you will see some slides that illustrate what a nice city Vienna is. I guess these kinds of pictures are probably taken only during shutdown times, because normally you would have hordes of tourists in front of this, the Palace of Schönbrunn, used to be the summer residence of the Kaiser in Austria, in Vienna. And I always start talks on amide activation with this very simplistic depiction that we teach students in introductory orgo, namely, how does electrophilicity at carbonyl compounds vary with structure? And you all know better than I do that acid chlorides and anhydrides are typically among the most electrophilic of carbonyl derivatives, followed by aldehydes and ketones, esters, and then typically amides and carboxylic acid or carboxylates tend to be down there in the confines of virtually no electrophilicity at the carbonyl carbon. One thing that we fail to impress in the same way in our undergraduate students is that another parameter varies in precisely the opposite sense, and that is the nucleophilicity of the carbonyl oxygen. Due to the donation power of nitrogen, of course, the delta minus at the oxygen carbonyl atoms of amides and carboxylates, of course, is the highest you can get in most carbonyl derivatives. And that has been exploited, among others, by Léon Gauzet in the 1970s and 80s in Belgium. Gauzet was one of the first persons to show that you could take a tertiary amide and formally dehydrate it by the action of a strong electrophile, triflic anhydride, and a base, typically a pyridine derivative, in this case collidine, to lead transiently to a species coined a ketiniminium ion. Gauzet demonstrated that these compounds undergo more or less concerted asynchronous cycloadditions with electron-rich double bonds to form 2+2 products in the form of cyclobutyl iminium ions, and of course, after hydrolysis, cyclobutanols. A few years after that initial discovery by Gauzet, André Charette published what is probably one of the most highly cited papers of the Canadian Journal of Chemistry, where he very nicely pinned down the mechanistic aspects of this activation process. So he figured out very nicely, using a combination of spectroscopic methods, that the first event is actually activation of the carbonyl oxygen by triflic anhydride, following something that you could call an iminium triflate. And that this iminium triflate is then eliminated of the elements of triflic acid by the pyridine base that accounts for the formation of the ketiniminium ion. But Charette also reported that it's very difficult to observe such a species in solution, since in the presence of the same pyridine base, you are able to engage an equilibrium that, of course, is strongly biased towards this pyridinium adduct, which is typically the kind of intermediate you can actually detect in solution. So our group started more or less around in 2009 to explore ketiniminium ions for rearrangement reactions, and we more or less compiled our group's work up to 2016 in this JOC Perspective article with Daniel Kaiser. And a couple of years later, we wrote a review on amide activation, which I would direct you to look for if you're interested in some of our earlier work. Today, I think it's way more valuable to look at the perspectives. Where are we going with this chemistry? What are our most recent developments? And in that regard, we have been very interested in this idea of a pyridine capturing a ketiniminium ion, because we figured out that if a pyridine is able to reversibly capture this species, so should a pyridine N oxide be able to do more or less the same. With the caveat that when you add a pyridine N oxide through the oxygen to a ketiniminium ion, you generate something which looks kind of funky in the sense that it resembles an enolate. But if you imagine a nucleophile approaching this species, it might actually be prone to nucleophilic attack at this center, followed by elimination of pyridine and generation of a new CO double bond with the oxygen that originally came from pyridine and oxide. In other words, we would probably be witnessing a polarity reversal from the typical delta minus polarized alpha carbons of carbonyl atoms to a delta plus polarity in this activated intermediate. This was actually based in preliminary observations reported by Gauzet in a footnote of a JACS paper the year I was born. And it's this kind of very simplistic mechanistic idea that really allows you to go a very long way. Because with this very simple proposal, we were able to do a bunch of things. For example, if your amide that gets activated by tryptophan anhydride, a base, and then captured by pyridine and oxide, carries an amide that has a benzyl group, then actually the benzyl snaps shut in a Friedel-Crafts type process, and you're actually able to form these types of quinolone or dihydroquinolone derivatives in relatively good yields, as reported in these two papers in 2017. What is also possible to do in this type of chemistry is to achieve formal alpha oxidation. If you use oxygen-based nucleophiles, you're able to attack the inolonium intermediate, we showed that in this JACS paper, and reach alpha hydroxy or even alpha keto products, depending on the nucleophile that you employ. When you think about cool nucleophiles that you would like to add, particularly in their nucleophilic form, to the alpha position of a carbonyl, I'm sure a lot of you probably are thinking of fluorine, right? If one think of something which is a nice nucleophilic species, but becomes kind of tricky to generate in its electrophilic form, fluoride might be probably among some of the most immediate thoughts that come to mind. And that's because fluorine really has a lot of interesting properties. There's a lot of industrial chemists in the audience. I don't need to school you on any of these. You probably know it much better than me. Fluorine as a replacement for hydrogen and even oxygen is a great strategy in MedChem, has a lot of impact on the properties of organic molecules, typically because it changes electronics, but doesn't really affect geometry due to the not too different size of fluorine compared to hydrogen. Of course, this leads to the fact that a sizable proportion of newly approved drugs every year typically contain at least one fluorine atom, and that placing fluorine in the beta position of an amine, for example, is a common strategy to, while reducing activity, increase bioavailability, and of course, massively increase stability towards metabolic oxidation, since you effectively remove one possible center for oxidation through oxidative metabolic enzymes. Of course, there's a whole side of fluorine that is also very interesting, and that's the one of F18 use in radiopharmaceuticals, right? And with its very advantageous properties, this is a great element for use as a PET tracer. With, of course, the key caveat, one would like, if possible, to use the negatively charged form, because that's what you get from the synchrotron, right? The big delivery that arrives with all these signals of radioactive material, watch out, is potassium fluoride. And so if you want to use fluorination methods that rely on F+ equivalents, you have to work quite quickly to convert that potassium fluoride into those labeled F+ equivalents before you can use them in your reaction. Wouldn't it be much cooler to be able to introduce fluorine into an organic substance using F-? That's pretty much what we were up to here. And I won't beat around the bush. The reaction works pretty much the same way as shown before. You activate the amide with tryptophan anhydride and a pyridine. Typically, we need to screen, and between most two halo pyridines, sometimes it's 2-fluoro, sometimes it's 2-iodo, sometimes it's 2-chloropyridine that works best. This is typically an activation step done at 0 degrees for a quarter of an hour. You then add the N-oxide, in this case, lutidine. N-oxide is our choice. You let it stir for 5 minutes, and then you quench the whole thing with 3 equivalents of the fluorinating agent. In this case, we settled for TDAT because you can actually get it anhydrous, and this leads to reproducible results. But as I'll show you in a moment, other fluoride sources are also suitable for this chemistry. What I really like about this type of activation is that it's extremely chemoselective. So we have a bunch of examples, 19 examples more, up to 83% yields. But the ones I've chosen to highlight here really represent something special about this chemistry. And that's because they are substrates where the amide is not the only carbonyl in the mixture, right? The amide is actually tethered to an ester, to a ketone, to a nitrile. And in all those cases, you observe alpha fluorination exclusively alpha to the amide with no affecting of the other carbonyl functionality in the molecule. Why is that so? Typically, if you do alpha functionalization of carbonyl compounds, you rely on enolate chemistry. But if you're doing enolate chemistry, there's no way you're going to be able to functionalize the amide before you functionalize the ketone or the ester, since those are way more CH acidic in their alpha position. But when you look at an electrophilic activation using the strong electrophiles such as trifluc anhydride, then the decisive factor is the amount of delta minus at the carbonyl oxygen. And in that competition, we already saw it in the first slide, the amide carbonyl wins hands down. And that's why you can have amide activation and amide alpha functionalization very selectively, even in a substrate that contains 1, 2, 3 ketones, which are pretty much spectators at this stage. Now, you notice also that the reaction times are very decent, right? Quarter of an hour, 5 minutes, an hour. This is no reaction where you wander around for coffee and then come back, right? And so we were wondering, can you actually use other fluoride sources? And we figured out, indeed, you can use TBAF. TBAF leads to slightly lower yields, but even after only 15 minutes reacting time, TBAF gives you a 70% yield of alpha fluorinated amide. You can even use KF. Of course, KF is not really soluble in DCM, but if you use a trick, namely to mix it with the cryptan, cryptofix 222, which solubilizes KF by sequestering the potassium, then you're actually able to, although in moderate yield, 60%, have fluorination in 15 minutes. And these are conditions that begin to be appealing to the F18 community, because this is a relatively fast fluorination reaction. And so we have already contacted and are currently working together with Veronique Gouverneur from Oxford, who's a worldwide expert in F18, so-called hot fluorination, to see in which extent this chemistry really translates to scenarios where you're using F18 labeling. But if you think about me as a naive organic chemist, I like the idea of being able to look at random organic molecules. I chose blockbusters, right? The blockbuster fungicide, piperylene, a blockbuster molecule that you might find around train stations worldwide, right? Fentanyl, a drug that led to Prince, or the artist formerly known as Prince, overdosing, and a compound that I always joke is probably very suitable for PhD students in the last year of their PhD thesis, citalopram, a blockbuster antidepressant by Eli Lilly. They are pretty different in their biological activities. They are pretty different in their chemical structure, yet I can look at each one of these structures and I can exactly know how to introduce one fluorine atom at a specific position of this structure, right? And actually you all know it too, because it's just a question of using alpha fluorination of an amide. In the case of fentanyl, the amide is still there. In the case of the other two, you just have to imagine the amide in your mind. We did that for all three of these compounds and more, and I want to show you the logic of this when it comes to citalopram. It's a relatively simple sequence of events. We use the commercially available precursor for the commercial synthesis of citalopram. This compound is available by the bucket. You deprotonate here with Booley, and in this case, you do a conjugate addition to acrylamide. This installs the amide, which you can use for fluorination. This gives a mixture of diastereomers, which we can separate. And if you are able to reduce the amide, again, the high selectivity of, or chemoselectivity of amide activation allows you to do the reduction of this amide, even in the presence of this nitrile here, which might have otherwise not really enjoyed things like lithium aluminum hydride, which probably comes to mind when you want to reduce an amide to an amine. And in doing so, we generated fluorocytalopram. The kind of coolness of this is not only that you're making a new compound, but it's that you're making a compound that was actually not even covered in the original Eli Lilly patent. Because I guess there was just no way of making it. And here we are having an access to this substance and not really knowing what it might do from a biological point of view. So this is the moment where you as an organic chemist can shine, go across the street, approach a colleague of yours that is a medical doctor who has no idea about organic chemistry, and tell him, we have a compound for testing which nobody else in the world has ever made. Colleagues like, what? That's no way, it's impossible, you have to test it right away. And so this is what this colleague, Harald Sitte, a good friend of mine and colleague from the Medical University of Vienna, looked at. And that relatively simple dose response curves, we can indeed show that we have lost activity. Remember what I told you? When you fluorinate beta-2-amine, you lose a little bit in activity, although in this case, it turns out that the fluorine appears to engage in an additional interaction with a tyrosine residue located in the binding pocket. But of course, the fact that you've done this fluorination results in a hugely increased metabolic stability. We are now finishing some pharmacokinetic studies on this that really suggests putting this fluorine here has a lot of benefits from a pharmacokinetic perspective, which might overweigh the fact that we lost six-fold activity from a point of view of dose activity, dose response curve. So you see this kind of logic that is all of a sudden unlocked just by the sheer fact of being able to place a random heteroatom at a non-random position. If you think about other nucleophiles one would like to add alpha to an amide, I would immediately think of enolates, because that would lead to an interesting approach to making 1,4-dicarbonyl compounds. We've done that, we've reported that in 2017. I won't bother you too much with details. It's pretty much the same reaction sequence. Replace the F- source with an active methylene substrate, or even a ketone enolate or ester enolate or amine enolate. This results in a relatively general synthesis of 1,4-dicarbonyls, which has its biggest Achilles heel in the fact that we have very poor diastereo control in forming an additional stereogenic center, right? Typically ranging from 1.3 to 1 to 2.3 to 1. And I always say ranging from lousy to a little bit less lousy. Still very chemoselective because you are able to again couple amides that carry other carbonyl functionalities with carbonyl enolates, and the reaction still proceeds pretty much in the way you anticipate. Now, you can imagine we got very excited by the whole thing, and we decided, boy, we have to try all the nucleophiles on the planet. We did. We tried all sorts of halides. You can do alpha halogenation if you want through this methodology. You can do addition of oxygen, sulfur, nitrogen nucleophiles. There's a wide range of those reported last year in a full paper in JACS. It's even interesting to use the nitrogen nucleophiles for a Smiles rearrangement, which means you can bring in a nitrogen that ultimately delivers also an electron poor aryl. And it's even possible to make a crossover from this type of stoichiometric amide activation chemistry into asymmetric catalysis, right? We figured out that it's possible in many cases to have as an intermediate the alpha triflate formed in a racemic sense, of course. But because these alpha trifloxy amides are highly reactive and are formed under relatively mild conditions, you can directly engage them in an antiselective nickel catalysis to do alpha substitutions that then result in products with relatively good to excellent enantiomeric excesses, as we reported also last year in CAM. So this is more or less the logic we've been up to in terms of reversing polarity. Again, very simple idea, goes a long mile. We then wondered whether there are other ways to reverse polarity, and of course, this led us inevitably to the chemistry of iodine-3, here symbolized by a gentleman who used to walk the same streets I walk to work every day in this wonderful city that is Vienna. If you have a chance to come to Austria, do not miss visiting Vienna and all its cultural beauties. And that's because iodine-3 really is as classical as Mozart's music when it comes to overcoming the natural polarity of carbonyl functionalities, right? You all learn in undergraduate organic that intrinsicum polum and catalyticum polum are among the most well-known strategies, using thioketals, using cyanohydrines or equivalents. But there's a field of redox polum to what, in some extent, you could actually consider our amide activation work to belong, but using iodine to form these kinds of iodine enolates, which are then really very straightforwardly displaced by nucleophiles with ejection, of course, iodobenzene, the quintessential living group of iodine-3 chemistry. And we, of course, being so fascinated with rearrangements, immediately thought, is it actually possible to leverage iodine-3 oxidation in these forms of iodine inoloniums? This just looks the same as I've shown you before, except the living group is not a pyridine, but rather iodobenzene, which are nothing else than syntons for an alpha cation, alpha to a carbonyl group, and now trigger some kind of rearrangement that places the positive charge somewhere else, leading to what you could consider a functionalization at a remote position, of course, with rearrangement of the skeleton. And one of our first works in this field used iodine-3 oxidation of silyl enol ethers that carry an aromatic group in beta. What we saw in those cases is that once iodine oxidation took place, the carbocation synton formally underwent engagement by the proximal aryl group to form these kinds of phenonium ions, which are then, of course, ring opened by the counter ion at the least hindered position, giving you products of distal functionalization and rearrangement, something we reported in Angewandte last year. And of course, when you see an aromatic, and you see an aromatic working well as a nucleophilic handle, you immediately think of using a double bond. Now, I have to say, when we imagined using a double bond for this, we expected a 3-membered ring product with nucleophilic attack at the distal position. And so we were pretty surprised by the observation that we actually formed another byproduct in small amounts when we use this alkene tethered silyl enol ether under iodine-3 oxidation conditions. We were expecting a Prims type reaction sequence to give us this carbocation, probably both of them in equilibrium. And at some point, we were wondering, let's form a cyclopropane with a mesyloxime substituent, since we use methyl sulfonic acid, methane sulfonic acid as the co-acid for this process. But as I told you, we got 8% of cyclobutane as a single diastereomer, something which is not expected by this chemistry, and which led us to do what I think were the decisive experiments, namely labeling experiments. When we labeled the terminal carbon either as a C13 or as a CD2 handle, we saw actually a 1-to-1 mixture, complete scrambling of the label in the final product. Part of the label was at the terminal carbon, as you would have expected to be. Part of the label was actually inside the cyclopropane. Same thing happens with the deuterium labels. You might question why it's not a perfect 1-to-1. It might have to do with primary versus secondary kinetic isotope effects. In any case, that there is a significant scrambling, to us suggested we are probably in the presence of some kind of non-classical carbocation rather than a Prims reaction intermediate, such as the one shown here. In any case, we first did what you have to do, which is a scope of this process using, of course, different substituents in this position of the silyl enol ether. You can actually rationalize some of these results depending on the Hammett constant, but also changing a little bit substitution patterns at these centers here, marked with 2 and 3, which of course lead you to slightly different substitution patterns in the final products. Now, if you have a process in which you suspect an intermediate being a non-classical carbocation, we just recently, I think, all saw a very nice paper by the List group on non-classical carbocation chemistry done asymmetrically with bronzed acids. There is one substrate which comes immediately to mind: advanced organic chemistry, non-classical carbocations. That's a norbornene slash chemistry, right? And so we wondered what would happen if you did an iodine-3 oxidation of a norbornyl silyl enol ether. Now, when you do that, you would expect, like before, to form an inolonium. The inolonium is a syndon for this carbocation, and according to a certain Saul Winstein's amazing work in the 50s and the 40s and the 50s, these should actually form non-classical stabilized 2-norbornyl cation. Those actually tend to evolve by loss of a proton and formation of nor-tricyclane. And that's indeed what we observed with a variety of different substrates. We indeed got direct formation of cyclopropane, effectively a cyclopropanation, a remote cyclopropanation, with relatively decent yields across the board. And most importantly, with little to no intervention of any kinds of rearrangements. We didn't lose a proton to get the alpha beta unsaturated ketone, and we did not rearrange the whole skeleton, as you might, in some cases of norbornane cation chemistry, observe. These are byproducts that were de facto not present in this reaction mixture, and the only things we saw were either the desired products or the recovered ketone through hydrolysis of the sialyl. And so, and if you see this kind of chemistry being possible by unpolung oxidation of a sialyl ether, then you have to wonder if the same thing is possible with an amide. And I think this is very nice because it closes the loop pretty nicely. What about using the corresponding amide and doing the same amide activation / unpolung I've shown you before, namely tryptophan hydride, pyridine and oxide. In this case, we again have an unstabilized enolonium. We do have a problem in that the leading group is a base, pyridine or lutidine or whatever it is, but we still hoped that we can also engage this chemistry to form nor-tricyclanes because we should still have a stabilized norbornyl cation. And indeed, we are able to convert these amides directly to the corresponding nor-tricyclane amides in a single step. Of course, in most of the cases, we observe now as byproduct the alpha beta unsaturated product that is kind of expectable if you are operating in the presence of a non-negligible amount of pyridine. But still, the reactivity of this intermediate is preferably towards formation of a CC bond rather than dehydrogenation and generation of an alpha beta unsaturated product, which I think very nicely rounds up this chemistry, because we went from making enoloniums through amide activation and exploring all sorts of nucleophiles for alpha functionalization into looking at this chemistry from a different perspective, namely a chemistry that can actually be used to do cool rearrangements that we first discovered using iodine chemistry. You can actually imagine what would happen if you did amide activation of this corresponding amide, not sialyl here, and how that actually allows you to use olefins or even activated norbornane CH bonds to form 3-membered rings under stereoselective regimes. So this is, I think, opening doors for a whole lot of new reactivity, and we're very interested in exciting this chemistry, exploring this chemistry further. This brings me to the end of my talk. I have, of course, a lot of funding agencies to think, also a lot of companies to think, very generously funded by Boehringer Ingelheim, but also by the ERC, the European Research Council, which is strong support since 2011, roughly 10 years of ERC support, without which we would not be able to do this chemistry. And of course, I myself don't really do anything. I tend to sit on my office, do emails, but also a lot of tweeting. The people who actually are responsible for all this chemistry are the heroes in this last picture. They are the ones who really, with a lot of enthusiasm and dedication, commit to this work. You see that a lot of their names in these slides. I like to emphasize the fact that they are a very diverse bunch of people. So we have people from more than 14 different nationalities in the group. And that's the way it should be, because if there is one class among our society that really knows the value of diversity, that's scientists. So we should never forget to advocate for diversity. I thank them for their very enthusiastic work in our lab. I think the Division of Organic Chemistry for this kind invitation to talk to you about our chemistry today. And I thank you all for your kind attention. I hope this was an interesting start for this last symposium. Thank you very much.
Thanks, Nuno. Great talk. Yeah, so there were a few questions that came in, mostly around fluorination chemistry. So we'll ask a couple and you can take the rest offline based on time. But What effect does different two halopyridines have? What drives the particular selection, and is there a rationale based on substrate?
That is like the million-dollar question in all this chemistry. So if I go back to the original, to the first slides, I hope the presentation doesn't collapse. So our current understanding is that the tuning of the two halopyridine still has to be done mostly empirically. So there's no way to say a priori, that's the one you have to use, that's the one you have to use. And we believe it really has to do with the position of this equilibrium. We've done a study in 2014 with in situ IR, where we've seen that although we cannot observe the ketene-iminium ion, no matter what halogen is here, or even if no halogen is there, there is a clear cutoff from a certain point on in basicity of the pyridine nitrogen that completely shuts down any possibility of this intermediate going back to the ketene-iminium and allowing nucleophilic attack. And so I think the halopyridine fulfills the role of maintaining a healthy concentration of ketene-iminium as low as possible, but high enough that you can actually engage it in further reactions. And that's why, depending on the chemistry, if you're doing sulfoxide rearrangements, if you're doing pyridine and oxide on polons, if you're doing tempo oxidation, depending on the chemistry, you will use a different 2-halopyridine because all those species have also different properties of their own. So it's not something we can say a priori which one you will need. And it's not something that is very easy to rationalize, although we do have a kind of a basic rule of thumb for which pyridines are more basic, which pyridines are less basic, and which chemistry you are typically working on, so that you can kind of calibrate for that. But I would not dare to say we have it all understood, because we don't.
Well, thanks a lot. That's really helpful. From YouTube, Marie Hoffman asks, really elegant, or says, really elegant, what about deuterium incorporation and an enantioselective version of the fluorination?
So let me ask deuterium incorporation. I didn't add it here. We just published on Chemistry European Journal that if you use DMSO, so if you actually add DMSO to this activated amide as an intermediate, you would be surprised to just recover the starting material. And you would think, did my activation fail? Did nothing happen? But if you label the oxygen of DMSO, you will find that label in the final product. So actually, DMSO adds to ketene-iminium ions and then proceeds to do a retro-ene elimination, which transfers one of the hydrogens of the methyl groups of DMSO to the alpha position of the amide. And that we demonstrated by using D6 DMSO as a way to deuterate amides, again, chemoselectively in the presence of all other types of carbonyl groups. This can even be used to do double deuteration if you just repeat the reaction twice. And we've just reported that in Chemistry European Journal. The second question about enantioselective fluorination, again, $1 million question. We have tried to do enantioselective fluorination using chiral auxiliaries on the nitrogen. That has been mildly successful because it's not that easy to really transfer chiral information from a chiral auxiliary to the alpha position. I still believe it's something that probably is best achieved with enantioselective catalysis, because we've seen with nickel catalysis how we can do CC bond formation enantioselectively. So I would hope that some work along those lines would be able to eventually deliver us an asymmetric alpha fluorination in the future.
Great. Well, I think in interest of time, there are a couple more questions I think you can answer via the chat, but I think we should move on to Neil.
Great. Thank you very much.
Thank you.
All right, thanks, Steve and Neil. Sorry, Nuno, that was fantastic. Great job. So now it's my pleasure to welcome Professor Neil Garg to today's symposium. I know Neil's really well known to the chemistry community, so I hope to keep this brief, and we're already getting kind of late. So Neil received his bachelor's degree from NYU, and then as a chemistry Padawan moved on to Caltech, where he earned his PhD in the Stoltz lab. After staying in the LA area, Neil followed up his postdoc in the Obermann lab at UC Irvine and joined the faculty in UCLA in 2007. Neil was promoted to full professor in 2013 and currently holds the position of distinguished professor. He's earned recognition for his work, for the work in his lab from so many organizations, too many to mention. But he does have several awards from the ACS, and in 2018 was selected as an ACS fellow. In addition to his history of developing key methodology and elegant syntheses, he's doing wonderful work to broaden the chemistry audience through things like his Bacon program and other teaching and outreach adventures, and I really salute him for that. Thank you. I reached out to some of the lab members in Neil's lab recently and received some feedback. Some of them heard rumors that Neil made it through grad school without caffeine. So amazingly, yeah, well done. But also, they all wanted in unison to mention the support that he has given him and the UCLA community during the recent trying times of 2020 with the pandemic and the fires in Southern California. So they all really appreciate that support that you're giving them. So, but this is not the talk you're looking for. So without further ado, I turn it over to Neil for his talk on strained intermediates and chemical education as vehicles for innovation.
Awesome, thanks, Scott. Yeah, I really appreciate the introduction. I appreciate you reaching out to my students. That's a new one, so thank you for doing that. And to my students, yeah, thank you for sharing that feedback with Scott and throwing me off my game here as I get started. I'll say that I agreed to participate in this virtual symposium. I think it was in January of this year. So it's kind of funny. I think at that time when I agreed to do this, I wasn't picturing doing it over Zoom in my bedroom. So it's a little bit different than what I envisioned, but hopefully it's still fun nonetheless. And it really is a great pleasure to be able to share with you some of the research that we do. And as Scott mentioned, I'll tell you both about some of the things we do in the area of strained intermediates, and I'll also tell you a little bit about what we do in the area of chemical education. And before I dive into that, I think perhaps maybe the most important thing I can do is take a moment to acknowledge and apologize to my coworkers. So just to start off, I have an awesome, amazing group of coworkers at UCLA. You can see they clean up well, and they know how to have a really great time, and they're just awesome scientists as well. And they work in a lot of different areas. You can see some of these on the slide, but the reason I want to apologize is because of the nature of this talk. I'm going to only speak about a very, very small fraction of all the research that they do. So my apologies to you all, and to anybody in the audience. I'd really urge you to check out our website and follow our publications and our research updates. Follow us on Twitter, and you can learn more about what all these wonderful people are up to in the lab. For the sake of time, I did want to focus the talk a bit and tell you about an area of research that we've been involved in now for many years, and that has to do with the chemistry of strained intermediates of the type shown here. And especially for students, if you're not familiar with this area of research, one thing I like to point out is that it's actually a subject area with a very rich history that goes back over 100 years. And so many people perhaps don't appreciate that the first time an arine intermediate of this type was thought about was back in the 1900s. So in 1902, Stormer and co-workers proposed the potential intermediacy of this benzofuranine, as it was called. And of course, this is an unusual thing to see because we're used to thinking about alkynes as being linear. And this was, turns out to be somewhat questionable of an assignment later, pretty much put into doubt. But on the bright side, it got people thinking about the idea, can you take a triple bond, put it in a small ring, and access that type of structure? It took about 50 years for that question to be answered in the context of enzyme. So both Roberts and Wittig, made breakthrough discoveries to validate the existence of this. And then a few years later, my apologies there, Roberts then validated the existence of cyclohexane. And so one of the questions that comes to mind, even now, I will get questions like this is, are these just obscure species that are scientific curiosities, or do they have real value? One of the ways that we can think about this and judge is just to look at what's happened in this area over the last 7 decades. If you look back in the 50s, there was perhaps just a few reports back then on this type of chemistry. And over the years, you can see a little bit of variability, but a real explosion in the last 10 years, 15, 20 years maybe, in the chemistry, you can see this from this curve, just from the SciFinder search. So there's been an enormous amount of effort in this area, and I think it is for good reason. And so, for example, if younger students don't really study this type of chemistry in the sophomore organic text, there are some awesome applications of what you can do. And I'll point out that now there's been many examples of using these types of strained intermediates to make heterocycles. There's many patents and in addition to papers describing applications to medicinal chemistry, plenty of applications in materials chemistry. And I also note a few key areas here. I think many people are familiar with ligands like XPhos, but perhaps most people don't appreciate that that is made through a benzyne reaction, okay, traced on to here, where ultimately these two bonds are formed. There's also examples of usage in the agrochemistry area. A prominent example comes from Syngenta in the synthesis of isopyrazine. So this is a fungicide, and these two bonds shown in blue are made from a Diels-Alder reaction of an arine intermediate. And then lastly, I'll just highlight the use in natural product synthesis. There are so many examples of arines and related species being used in total synthesis to date. I just highlight one example from my friend Richmond Sarpong up at Berkeley, where you can see a absolutely intimidating and daunting structure here where an arine intermediate turned out to be quite useful. So I encourage you to check out any of these in further detail, but hopefully you take my word for it that these types of intermediates actually have some significant amount of practical value. And so when my lab began, we had some, I'd say, relatively simple ideas at the time. Can we make heterocyclic arines like indolines and pyridines, recognizing the importance of these scaffolds in the pharmaceutical sector and natural products as well? We had ideas that we would ultimately explore for how to use that chemistry to make very highly sought after targets called the well-written dolinones. And then along the way, we were able to learn quite a bit about reactivity and principles of selectivity and turn that into reliable predictions using something called the arine distortion model. And this has just been an awesome and wonderful collaboration with my good friend and colleague and collaborator, Ken Hauk at UCLA. And just to give Ken a quick shout out, he is the recipient of the Roger Adams Award for 2021. So we're really thrilled about that at UCLA and very much like to congratulate Ken. So in terms of the chemistry I wanted to share with you today, that gives you a little bit of context for why these types of intermediates are important, why we got into this game. But what we've been doing in recent years is to shift away from the arines, right, these aromatic strained alkynes, and start moving into these types of versions that don't have aromaticity. So what about cyclohexyne, cyclopentine, heterocyclic versions of those? And then can we also start to think about cyclic amines of this type? And part of our motivation here is to move away from those aromatic compounds, the so-called flatlands, and get to accessing scaffolds that are more sp3 rich. So that has been a big interest and motivation from our standpoint. And in particular, we've also been very interested in looking at derivatives of these two types that I'll tell you about today, where we can put nitrogen in these types of strained intermediates, ultimately thinking about these as precursors to make substituted piperidines, which are incredibly important for pharmaceuticals. So actually, the real story I want to tell you has to do about cyclic amines, but in order to introduce some of that chemistry and perhaps share some chemistry that may be useful to those of you in industry especially, I wanted to give you a sense of, well, how do you think about making an intermediate like this? Let's call this a piperidine. There's a lot of different ways that one can consider making this type of structure. The typical methodology we use is known as the Kobayashi approach to make these types of strained intermediates. So these intermediates, you will see them drawn throughout the talk. One thing I'll point out is that we never isolate or observe them. Instead, we infer that we've intercepted them by virtue of the starting materials we use and the products that are ultimately formed. And so the simplest way we can access them is to come in with a substrate that has a double bond in place. On one carbon, we have a triflate as an excellent leaving group. On the other carbon, we have a silicon substituent, very often trimethylsilyl group. And the idea behind this Kobayashi approach, right, which was first explored in the context of benzene that we're now applying here, is that the fluoride will attack the silicon. That leads to formation of the triple bond with loss of that triflate leaving group. And this is just a process that happens in situ. In terms of the chemistry, the way we run these operationally is actually very simple. So if you haven't done a strained intermediate reaction using silyl triflates, it's really remarkably simple. you take the substrate, add it to your solvent. In the presence of a trapping agent, in this case an azide, nothing will happen, but once you add the fluoride, that will initiate formation of the strained intermediate, which then undergoes trapping, right? And often will lead to a regioselective cycloaddition. So for example, in the azide cycloaddition, you can see the product that's formed in 81% yield, and the numbers you see here are the ratio of regioisomers formed. And just to highlight this again for the medicinal chemists, is that you can take that same substrate, you can use different trapping agents, whether they be diazoesters, nitrones, or others that we've used. And you can use those to make different types of heterocyclic products, all using this type of strained intermediate chemistry. And if you are interested in using this, I'll point out that Sigma Aldrich does sell this silyl-triflate as well as some of the precursors to it. And so it is actually quite easy to use and to adopt, right? So hopefully it's practically relevant for some of you. If any of you have questions about this, I'd be happy to tell you more about this. But I hope you also take away that the chemistry is relatively simple. It relies on these silyl-triflates and the cesium fluoride promoted reaction to ultimately form that strained intermediate. So now, as we think about this arine and cyclic alkyne chemistry, it's pretty powerful because you can intercept that strained intermediate, you can build 2 new bonds. But why don't we think about doing similar chemistry with a cyclic alene rather than an alkyne? Just like an alkyne, it could potentially undergo cycloadditions to build 2 new bonds, but now we also have the possibility of introducing a stereocenter, which we thought presented an exciting opportunity. And I'll tell you, people still give me dirty looks if I show them a structure of a cyclic alene of this type. And I always first reply saying that, whoa, we're not the ones who came up with this crazy concoction. This is actually chemistry that has its foundation with the great George Wittig, who, as many of you know, received the Nobel Prize in '79. But less well known is the study in 1966, where bromocyclohexene was treated with t-butoxide to make the cyclic alene, presumably formed in situ, because in the presence of trapping agents like this diene, they could access this product. You can see the yield is modest, but a critical proof of concept suggesting you can make this type of intermediate. There have been many theoretical studies over the years. I cite some by Ken Houck and Richard Johnson. And with regard to synthetic chemistry, I'd say this field is really one where there have been efforts, of course, but some of the ones that have really led to increased synthetic utility are perhaps this one by Guitian in 2009. And then our lab and the West lab have also looked at different types of cycloadditions, including in West's case, some pretty cool intramolecular reactions, if anybody's interested. So we were very excited about this. Can we make these types of intermediates? And can we also consider AZA versions instead? Can we make substituted versions? Would those undergo cycloaddition reactions, again, to build new bonds and perhaps to annulate the scaffold? Could we perhaps set stereocenters? And how would these substituents impact all these parameters? We then have to ask questions, well, how are you going to make this in some sort of a mild way that allows you to explore the reactivity? And what we settled on is using this Kobayashi type approach again. So let's just say we want to build 2 of these double bonds. One of them is built in over here at the top. And on the proximal carbon, you can see that we have the silyl and the triflate. And just like we said before, we hope that the fluoride will lead to elimination. And I'll point out that, again, this is the Kobayashi approach, but Guitian had also demonstrated this in the context of 1,2-cyclohexadiene. So this seemed like a very viable approach to access these azacyclic alene scaffolds. This project was really led by Joanne, Michael, Melissa, Evan, and Rachel. And a close collaboration with Ken Houck, we made several different types of cyclic alenes. You'll see results for 2, or at least one of them, or 2 of them today. And I won't show you all of these results in the interest of time, but I will say we have looked at 4+2, 3+2, and 2+2 cycloaddition reactions, and you can actually build some pretty cool scaffolds using these types of intermediates. Some people might wonder, what are the structures like for these compounds? I think many of us are more comfortable with linear allenes. Okay, so there you can see that angle is 180 degrees. These are planar. Again, we think about these as being 2 pi systems that are orthogonal. And so people then wonder, what is it like when you take that and you put it into a ring? What you do is, of course, you lead to severe bending. You can see the internal angle here is now 133 degrees, so it's no longer linear, of course. It is significantly bent that introduces almost 30 kcals per mole of strain, leading to this being a highly reactive species. And one thing that I think is pretty cool that I'll come back to in a moment is that these species are chiral, just like linear allenes. And you'll see how that leads to, I think some opportunities for methodology development and also synthetic applications down the road. So I'm going to do a disservice to this project by not going through all the synthetic experimental results. It's a lot of work to make the silyl triflates or to figure out how to make those and then do the trapping experiments. We have published these results, so I won't go through them in the interest of time. But instead, I'll point out that depending what type of substituent you have on the cyclic allene, you can actually modulate regioselectivity. So if you have an electron donating group, it's the double bond distal from that, in this case, the methyl, that undergoes reaction with an electron-rich diene. If you have a withdrawing group, it's the double bond proximal that reacts. And then if you have something that's fully substituted, you'd expect that these two could work in concert, those two effects. And in fact, that's what we see. We're able to trap out this cyclic allene where the reaction occurs on the double bond, both distal to the methyl group, proximal to the ester. This is one example using a Bach protected pearl. You can see the reaction works in 81% yield. All right, so it's a regioselective reaction, so specific for this double bond isomer. It's stereoselective, it's diastereoselective. We form a product with 3 stereocenters. And that's through the formation of 2 new bonds. And by the way, one of those stereocenters that we just made is a quaternary center. So I hope you take away a couple of things. It's a little bit of an unusual way to think about making a heterocycle like this, but from a practical level, if you have access to the silyl triflate, the chemistry is very easy to run and you can build some cool things and the reactions are selective. And ultimately, as we learn more about them, they become more predictable as well. One of the things that's really been a point of fascination for us recently has to do with thinking about stereochemistry and thinking about absolute stereochemistry. So we couldn't help but wonder, would it be possible to make something like this type of cyclic allene and enantiomer enriched? And if you made it, would it be configurationally stable? Would it racemize? How likely would that be? So Melissa, who's actually a joint student with Ken, she looked at the racemization barrier here, estimated that to be about 16 kcals per mole, which was interesting because that's around in the same vicinity of the barriers we predict for cycloaddition reactions of these types of species. So it's sort of that perfect point where it begged us to run the experiments to see what would happen. And so we started to ask the question, how do you make a cyclic allene like this in an enantiomer-enriched form? And we wondered, maybe we could trace that back to our silyl triflate, where perhaps we could set the stereocenter at this position. And what we did here is we actually prepared this, a precursor to this using chiral separation. And then we went ahead and ran this experiment to see what would happen in terms of EE in the product. It turns out that in 73% yield, we can isolate the product and you can see the EE is about 90%. So it's pretty cool. You can actually transfer a significant amount of that stereochemical information. And notably, we're starting with a compound that has a stereocenter here. So it has point chirality. We transmit stereochemical information to the cyclic allene. That's now an axially chiral species. And then in undergoing the cycloaddition, we arrive at this product. Again, we form 2 new bonds, but importantly, we've made 3 stereocenters now in the absolute and relative sense. None of those stereocenters are present in the starting material. And in fact, the only starting stereocenter we had at the beginning has been ablated in that process. So it's a pretty unusual reaction, ultimately shows the idea though that you can transmit stereochemistry from the starting material to the product. One of the opposite way to think about this that we've been really intrigued by recently is, wouldn't it be cool though if you didn't have to set that stereocenter to begin with? What if you could come in with that silyl triflate being racemic, all right? Access the enantiomer-enriched, the racemic cyclic allene, and hopefully these might be able to interconvert, and perhaps we can modulate that with substituent effects, right? And then perhaps if we do a trapping experiment using transition metal catalysis, maybe one of these could react faster than the others in a dynamic kinetic resolution, ultimately leading to an enantiomer-enriched product. And it really got us excited. Can we take cyclic allenes, these relatively obscure structures that have been known, I think, since 1966, and now in the modern era, use these in asymmetric transition metal catalysis? When we take a step back and think about the state of these strained intermediates and things like benzynes and cyclic alkynes, when we started to look at this, there was very little in the literature. I think the pioneering study is this one by Guy Tian and co-workers in 2006, where it was reported that they performed a 2+2+2 cycloaddition reaction using palladium and BINAP. And you can see they're able to access this product in modest yield, but in promising EE, 67%. So to us, this was very exciting, and this was the state of the art when we began. There were no examples of cyclic allenes being used in asymmetric catalysis, and in fact, there was only one example of a transition metal catalyzed process involving a cyclic allene. So we got really pumped up about this. In terms of a reaction design, and to think about this as a proof of concept, again, we want to start with the cyclic allene. That's going to be racemic. And we want that to then somehow encounter an organometallic species. And because benzotriazonone denitrogenation processes were known, both using nickel and palladium, we thought we would start with the benzotriazonone here, use nickel 0 to blow out nitrogen, access the nickel cycle shown here. And this becomes the key challenge because the cyclic allene is a fleeting intermediate, and again, it's racemic. And now that needs to run into or encounter a catalytically generated organometallic species. We want the chirality on this ligand to control this process to undergo a selective olefin insertion reaction. And then from here, if this were to undergo reductive elimination, that would give an enantiomer-rich product. So that was the vision. And again, there were many processes like this known. I'll definitely give a shout out to Masahiro Murakami, who had in particular developed reactions of linear allenes rather than cyclic allenes in this area. That was absolutely instrumental in our design. So here's another point where I need to apologize to the coworkers who tackled this project, just a Herculean effort that went into this. The project initially conceived by Maud, Brian worked on the racemic variant, and Michael and Andrew, shown here, just did an awesome amount of experimental work on the asymmetric reaction and a lot of creative thinking. Ken's group brought a power team of computational chemists that were able to evaluate various mechanistic pathways. So this was really been a wonderful collaboration that led to a lot of insight. I think in the interest of time, I'll just show you briefly one aspect of the computations, and I'll leave the rest as a little bit of a teaser for you. The key thing that we were, I think, super curious about at first is to examine that important step that I mentioned, the olefin insertion. So are these intermediates rapidly interconverting, and then do they undergo olefin insertion reactions? And how do the barriers look competitively? It turns out that we do think that the process can occur in a stereoselective way. So for example, the barrier for olefin insertion on the pathway on the left, that barrier is calculated to be about 7.5 kcals per mole. And then the alternative pathway we see is 14.9 kcals per mole, so more than 7 kcals higher in energy. So that key question of, can you use asymmetric catalysis to discriminate between the two faces of the cyclic allene? We do think, in fact, that is possible. One of the curiosities, though, is that how do you get from that olefin insertion intermediate to the final product? And is this reductive elimination viable? So that's what we initially proposed from the simplest pathway to get us to the end. But in fact, the calculation suggests that the barrier here is pretty high, 37 kcals per mole. And also, interestingly, when we work through and figure out what the major enantiomer is, it turns out that if you were to follow this pathway, that would give the S enantiomer, which is not the major enantiomer that we observe in these reactions. So instead, what we propose happens here is that the eta-1 complex is in equilibrium with this viterionic eta-3 complex. And then from here, this undergoes desymmetrization. You can imagine attack at carbon 1 or carbon 3. And to make a long story short, we think that attack at carbon 1 is favorable by about, attack at carbon 1 is favorable by about 1.5 kcals per mole. And that actually correctly predicts which enantiomer is formed. And it's pretty good at estimating the sense of enantioselectivity as well. So this has just been an awesome study. I think it validates that you can use cyclic allenes in synthetically useful catalytic asymmetric reactions. And it also provides at least two different ways to think about how to establish or control absolute stereochemistry in these types of transformations. So hopefully you'll see more work in this area in the future. And I hope what you can take away from this is, certainly the minimum a reflection on the rich history here. As I said, these intermediates have been around for a long time, the 1900s to the 1950s. And if you fast forward to 2020, you can do some pretty remarkable things. You can synthesize heterocycles, you can functionalize them, you can build amazingly complex structures of the type you've seen here. And then, as you saw moments ago, you can do things like transition metal catalysis, asymmetric catalysis, dramatically expanding the scope of perhaps the more traditional cycle addition reactions that have mostly dominated in the field. Right, and it looks like I'm already running short on time. So again, I'm going to keep the end part here relatively brief, and just say really quickly something important about education that is really a call to students. And that's just to say that when I started at UCLA, the last thing on my mind was education, right? Everything I cared about in putting together my application, interviewing, and getting startup package had to do with research, making sure I had the funds needed, making sure I would have enough students, all those things. And it wasn't until I actually started teaching large undergraduate classes, like 400-person classes, that I realized that education is really not a burden. It's perhaps one of the most important opportunities that we have. And so I invite you to visit our website, and you can see some of the different tools that we have developed. But we've really had a huge emphasis on developing things that can be used all around the world. And one of those initiatives has been to think about how to help students visualize molecules in 3D. And some students actually asked, these are undergraduates, they said, Neil, why do we have to buy a model kit? We pay $20, $30, whatever it is for a model kit. We use it a while. I can't really use it in the lecture hall. Why do we have to do this? So I said, of course, well, hey, if there's some value for building the molecule, et cetera. And they said, look, I should be able to do this on my phone. And I couldn't really argue with them. And so what we did is that we developed this website. And again, I'll invite you to visit on your own time. It's called qrchem.net. And what it does is it allows you to generate these QR codes. You can take these QR codes, put them in a lecture presentation, put them on a poster, whatever you need to do, and then students can scan them. And if you scan this one, you can do it with an iPhone camera or an Android if you have a QR code reader. If you scan it, what you end up seeing is something like this. And this is an interactive depiction, actually a screen recording from my own smartphone. And you can see that you can picture actually what a cyclic alene looks like. That's not something that, by the way, you would have an easy time building with your molecular model kit. So you can rotate it around and appreciate better what that structure looks like. Use one finger to rotate, 3 fingers to translate, move it around the screen. And if you pinch, you can zoom in and out. I'll say that a lot of this website is about instructor resources. And you can see my students have made these awesome slides, lesson plans. You can teach like VSEPR theory using this tool, for example. Plenty of organic chemistry. And now you can also generate your own QR codes either from an NIH database or through custom. All right, and then lastly, I think one of the things we should be pursuing as a field is to think about virtual reality when it comes to manipulating molecules. And I'll just say that during the pandemic, this is something that my students and I have gotten really, really into. Is to think about not just how you visualize molecules, but how you interact with them in 3 dimensions through a virtual experience. I'll show you a screen recording of something. My disclaimer is that the video is nowhere near mimicking what the actual experience is like. So please take my word for it that this is way cooler than what you see here. So if you were thinking about what a cyclic alene looks like and you entered a virtual environment, you can see a simple depiction. And look at that, it looks like there's also a cyclic alene just happened to sitting on a little bit of a trophy shelf right there. You can pick it up with your virtual reality controllers. You can move it around, okay? You can actually do anything with it. You can move it around, you could zoom in and out, you can enlarge it, you can make it look like it's 3 stories tall. And you can quite literally walk around it, you can go inside it, whatever it is that you might like to do. In this case, if I was curious, what does a cyclic alene really look like? I can hold it up right in front of me. I can stare down those 2 pi bonds, right? And look at those angles around where those hydrogens are, twisted a little bit out of plane. And then if I really want to have some fun with it, what I can do is think about that Diels-Alder reaction. How would that work? And if, well, look at that, there just happens to be a furan in the same virtual environment. So I can pull that die-in over, line it up in an endo transition state, and have some sense of what it might look like. And so hopefully, Ken, if you're watching, you're thinking about how do we do this all with transition states? And sure enough, I think all of these things are really quite possible. So I think this is the next generation of learning. You can imagine virtual class, people have their own devices as these things become cheaper, or you can imagine post-COVID that you could have a series of these available in a department available to your students. So hopefully that gives you a little bit of a teaser of some of the things that we're doing now in the space of education. I'll say again, it's incredibly important that we as a community tackle these types of initiatives. The efforts that my students have been able to undertake have easily impacted on the order of 1 million people in over 6 continents and 165 countries, all information made available to us by Google Analytics. So with that, I will leave you with some smiling photos and say thank you to the people who have just been amazing. Dan Caspi, old friend from grad school, IT wizard, absolute wizard, and his company Element 26 does all of our IT solutions for all these educational initiatives. These undergraduates you see at the top are the ones who developed QR Chem initially working with Dan. And then graduate and undergraduate students shown here, especially Francesca, Jason, and Melissa, have been an absolute force with the virtual reality. And Melinda and Matt were big players in QR Chem. Matt also helped with something called the OChem Reactivity Book, a kid's book available for download on the website. And you can see many others in the lab have contributed to the QR Chem effort along the way as well. So I greatly thank you for that. You saw that the group is a really wonderful group. We know how to work hard. We also know how to play hard. For whatever reason, we're dressed up as pirates. I guess we thought it was a good idea at the time. And yeah, it's a really wonderful group. We appreciate these agencies who fund us. I showed photos and names of the people who did the work that I talked about today, so I won't spend more time on it at the moment. Just to say that I am very grateful to any of my students who are watching for all the things that you do. And again, apologies for not being able to talk about all of your Herculean efforts and really creative efforts on a lot of different projects over the years and currently for the current group as well. I'll leave you with some smiling photos of some of my colleagues and just say that UCLA is an absolutely incredible place to be. My colleague Mike Jung has discovered not 1, but 2 drugs to treat prostate cancer. This has been instrumental for UCLA. And with regard to the future of organic chemistry at UCLA, it's looking bright. We have 2 of, I think, the most exciting young professors in organic chemistry. That's Hosea Nelson and Alan Sutton. So if anybody's interested in UCLA for graduate school, postdoctoral studies, I certainly encourage you to give us a look. It's a really exciting time, certainly for me. And so with that, I know I've overstayed my welcome. Scott, thanks for not muting me and cutting me off the stage. I really appreciate the opportunity. I appreciate your attention. I'd be happy to answer any questions.
That was great. Thank you, Neil. That was yeah, that was super. Really exciting stuff, and I really like that combination of the transition metal catalysis with the alleys. It was something I could easily see us taking a look at. Couple questions online for you. One from Nick Chapini says, how critical is the identity of the silo group to the efficacy of the cyclic alene generation, whether using TES or TMS or TPS? Has that been explored?
Yes, is the short answer. So let me, if you don't mind, I'll pull up a slide to answer the question and keep people on the same page. Okay, hopefully folks at home can see that. And the question basically has to do with when you're thinking about silotriflates, doesn't matter if this is a TMS or a TES. I'll say sometimes in the substrate synthesis, we've observed proto-desilylation. And so just in terms of making the substrate, sometimes we make the triethyl silo version just to avoid that undesirable proto-desilylation in the synthesis. In terms of the actual strained intermediate chemistry, what it typically affects is the temperature that we run the strained intermediate generation and trapping experience on. So basically, the bigger the silo group, the slightly slower the reaction. But certainly in the context of benzene, people have compared TMS versus TES, and we've done some similar things in the group. But in short, you can mostly interchange, in some cases, TMS versus TES.
Excellent. Okay, one from Trevor Harris saying the endocyclic CX bonds in the cycloalene cycloalkynes could potentially be good sigma acceptors to the donor pi system. Do you see better orbital overlap for the alene or the alkyne?
For the alene or the alkyne, could potentially be good sigma donors to the. Yeah, I guess I'm not sure if I completely follow the question, and I don't know if I can, even if I did, I think I may. I'm starting to understand the question, but I'm not sure if I have the means to give a direct answer to that one at the moment.
Okay.
Yeah, if any of my students are there, or Ken or Melissa, if anybody wants to take a stab at that, feel free to throw it in the chat. But I'm not sure if we have a good way to compare that.
And there is another one from Phil Moss on YouTube for about while you were using the VR, which I thought was amazing myself. It's really cool. That and the QR cam is just, yeah, gonna be a nice, real game changer. Can you break and form the bonds while you're playing around with the molecules?
Yeah. So can you break and form the bonds? No, not yet. It's you know, they're really in the virtual mode. Those things that we're bringing in, they're treated as individual objects and they can't be manipulated, except for moving them, rotating them, things like that. But in terms of like breaking a bond or yeah, doing things like that, you can't really do. I mean, you could overlap two objects and things like that, but yeah, we can't break bonds yet. Cool idea though.
And one from Bob Grossman. How much diradical character do these cycloalkenes have?
The cycloalkenes?
No, sorry, cycloalene. Sorry,
cycloalene. Sure. Yeah. So, Bob, you know, I think when I heard a question from Bob Grossman, I missed Bob Grossman, Kentucky.
Exactly.
Because that's how he used to do this at Gordon conferences for his 1,000 questions he would ask. So, Bob Grossman, I hope all is well. And we all obviously still use your mechanism book at UCLA very much. So, thank you for that. Yeah. So, it's an interesting question. Bob, I think it varies depending on the cyclic alene, and these have been studied quite a bit computationally. And one of the references that I mentioned earlier, I think here, probably some of the work of Johnson explores this a little bit more. So I guess I'd point you to that. When we look at the calculations for these reactions, typically for the transition states, you know, for example, Melissa's, I think on the call, Melissa would typically look at stepwise processes, you know, concerted, asynchronous, concerted, synchronous, et cetera. So typically we will evaluate all those processes in a given reaction. But, you know, in terms of how they react, it may also vary depending on what the trapping agent is. But if you're interested in the structures, I think Johnson has done a nice job of evaluating those and also looking at that as you change the ring size.
All right, well, that looks like about it right now, and we are spot on time. So I just want to say thank you so much to both of our speakers today. Thank you, Neil. Thank you to Nuno. Thank you to Steve for putting together the intros, and all the folks, Rio and Denise and Hugh from the CCHF for supporting this, the ACS Organic. Just a tremendous program that's been going on. I'm really happy to be a part of it. Thank you very much. Thank you, gentlemen, for your talks today. Thanks to all the participants. I think we were up over 300 on YouTube and almost 100 on Zoom, which may be a low estimate because people watch in rooms. And really, yeah, just thanks for being here. Thanks for enjoying it. And thanks for being part of this awesome series.
Thanks, everybody.